as we talk about circular functions and their graphs. I told you to make sure you keep up with Radian measure. I mean, in your calculator, that you pay attention to whether you're in radians or degrees. Anybody already know what radian measure is? I bet Sinead does. But the rest of us, maybe, maybe not. Whenever we talk about it, you might go, oh yeah, I think I've heard of that before. If not, it's not a big deal. All it is a tool that will let us measure basically in something that's unitless, okay? Degrees is a way of measuring, but a degree is a specific unit because it takes how many degrees to get a full circle? 360 degrees. But there are other ways of measuring. So if we want to talk about something that has a unitless measure, that's when we want to use radians. And the definition they're going to give us is that an angle with its vertex at the center of a circle, so one like this, that intercepts an arc on the circle equal in length to the radius of the circle. Okay, so in other words, this radius right here, we're going to call it a length of r, okay, because it's our radius. Then we're going to say that this would end up being whatever our sector length is divided by that radius, okay? Oh, I'm sorry, I got that in the wrong spot. Yeah, well, that's in the right spot. I was actually doing this up here. That it's equal in length to the radius of the circle has a measure of 1 radian. Sorry. Okay, so in other words, that we're able to look at a circle. If it comes all the way around here, then we are looking at a length of 1 radian to go halfway around a circle. We're going to have I'm sorry, not 1 radian to go halfway around the circle. It will be 1 pi radians, okay, to go halfway around the circle. A full circle is going to be 2 pi radians. So if you look right here, this is just kind of giving you some visual on if this length right here is half of what the radius is, we'd say that's half of a radian. If this has the same length as 2 of these radii, then that has 2 radians, okay? And when, like I said, for a full circle, it's going to be 2 pi radians. Now, the ratio S over R, where S stands for your sector length, R stands for radians, okay? And they're in the same unit, because if I was measuring this, okay, whether I'm using inches, whether I'm using feet, if this is also measured in inches or feet, when I make that ratio, what does the unit do? What would inches over inches do? They're the same, so wouldn't they cancel out? Because anything divided by itself reduces down to 1. So that's the point of this, why it's a unitless measure. It is not going to have anything, any kind of unit with it, like feet or centimeters, because the units actually cancel out, okay? So we can convert between degrees and radians really easily as long as we understand what those conversions are. So I already mentioned 360 degrees is a full circle. In radians, do you know how much that would be? 2 pi radians. Okay? So I can change things from degrees into radians or vice versa if I know that. Now, if I don't have 360 degrees, but I only have 180 degrees, then what would that mean? 180 is how much of 360? It's, yeah, because it's only half. of this. So half of 2 pi is just pi radians, isn't it? Does that make sense? Okay. And 1 degree would be, this is the way that I would figure it out. Okay. 1 degree, I'm going to multiply this. This is the way I would do these conversions. I'm going to multiply it by the ratio that would make degrees and radians equivalent. And I want to do it in such a way that if I have degrees on top here, I'm going to want degrees on bottom here. Remember when we did like those revolution questions where we had to go from, say, revolutions per minute to feet per second, and we had all those unit conversions? That's the idea. My unit conversion is going to have to be equivalent to 1. And the only way that I can write these where they're equivalent, and it's going to let me change this, is if I put degrees where? On top or bottom? I want to put them on bottom, so that will cancel out. And that would mean 360 degrees on bottom is the same as how many radians on top? 2 pi. Now, what that will give me is something I can now simplify. I know the degrees are going to cancel out. What can I do with a 2 on top and a 360 on bottom? Will that reduce? Mm-hmm. And remember, pi is a number, but it's an irrational number. So we're just going to leave the symbol pi there. But 2 would go into 360 180 times. So 1 degree is the same as pi divided by 180 radians. Okay, makes sense? Now, let's see if we could get a conversion that would explain what 1 radian is in degrees. So if I have 1 radian, how am I going to set up that unit conversion? What do I need on bottom now? Instead of the 360 degrees, I want to put the 2 pi radians on bottom, and I'll put 360 degrees on top. And that means this is going to turn into what? Notice the degrees doesn't cancel out with anything. That's why it's still here. What can I reduce down? 360 over 2. And 2 goes into 360 180 times. So 1 radian is equal to 180 divided by pi degrees. Okay, so those are our conversions. Honestly, as long as you keep up with 360 over 2 pi or 2 pi over 360, you shouldn't have trouble converting from one to the other. All right? So let's see if you can tell me how you would do this. If I want to convert between degrees and radians, then what's my ratio going to be like that I multiply a degree measure by? If I want to go from a degree to get to a radian, then let's look at what we did and talk about this. In both of these cases, when we use the 2 pi over 360 or the 360 over 2 pi, they both reduce down to this ratio. I've got pi in one place, 180 in the other. So rather than do 360 over 2 pi, this is the reduced form of it, right? So you tell me, if I want to go from a degree value to radians, which way do I set up the conversion? What do I want on top? What do I want on bottom? That is correct. Pi on top, 180 degrees on the bottom, so the degrees would cancel out. That'll take it to radians. If I'm going from radians back to degrees, I have to do what to this? Flip it. You got it. That's all there is to it. Okay, so let's try to do a few conversions. I want 108 degrees to be changed into radians. So what would I need to multiply by? All right, let's do pi over 180. Now, do you think we can reduce down the 108 and the 180 somehow? Yes. I think we can. I mean, clearly they're both even numbers, so I know they've got some sort of common factor. Do you think anything else that would go into them besides 2? Or do you just want to start with 2 and see where we end up? 9. Okay, so 9 would go into 108 how many times? 12 times. 9 would go into 180 how many times? 20. Okay, that's better, but we're not quite finished because what's going to go into both 12 and 20? Something bigger. 4. I can divide 4 into 12 3 times. 4 goes into 20 5 times. I think I'm finally reduced down. What's this going to turn into? 3 times pi over 5, and that's in radians. Okay? All right. Can we change negative 135 degrees? Is it a problem changing a negative measure?
Just the same way.
We should be able to do it the same way, wouldn't you think? Okay, so we're going to multiply by pi over 180. All right, so we got to figure out what we're going to both 135 and 180 evenly. Clearly, they're both divisible by 5. You think we have anything bigger than 5? You want to just start with 5? Okay, so 15, we can do 135 divided by 15. Oh, wait, oh, I did 125. Yeah, 135 divided by 15 is 9. And then 180 divided by 15 is 12. So we're definitely better. We're just not quite there yet. What else can go in? 3. So 3 goes into 9 3 times. 3 goes into 12 4 times. What would this equal in radians? Excellent. Negative 3 pi over 4. Don't lose your negative sign. All right. What about 325.7 degrees? Can we still multiply that times pi over 180? Yes, we can. Now, let me explain on this one. Since this is a decimal value, that's not going to reduce down cleanly, is it? Okay. And do we have a decimal approximation we could use in our calculator for pi? Yeah, if you'll notice, you have a key on your calculator. If you're using one of these, it's this button right here. If you use the second, it gives you pi, which will, now remember, since it's irrational, it's a decimal number, it doesn't end, doesn't repeat. So it's better not to use just 3.14. You want to keep as many digits as you can. And if we put this in the calculator, we could multiply 325.7 times, and I'm going to pull up pi, hit enter, and divide that by 180. And this would be, since we have 1, 2, 3, 4 digits showing here, let's include 4 digits in our answer. And that would be about 5.68, what would need to be my last digit? 5 radians. Okay, so there are times that you will use the calculator approximation for pi if something doesn't clean up neatly. But remember, this is exact when we leave pi in it. This is approximated, okay? So if they give us something that is already kind of in decimal form that's not going to reduce down cleanly, you're probably going to have to do it this way. And the computer instructions should be clear on how you would enter it. I think you would see a different instruction on this as opposed to this. Okay, this would expect you to give an exact value. Now let's go the other way. Let's start with radians and see if we can get it into degrees. So if I have, and for some reason, I don't know why it put P there instead of a symbol. There was a formatting thing when this printed out. Make those pi's where it says P. Okay? And so if I have 11 pi over 12, what would I multiply by to change it to degrees? 180 over pi. Good. And my pi's will cancel. What else can I do? Yeah, let's see. 180 divided by 12 goes evenly 15 times. And how much is 11 times 15? Good, that is 165 degrees. 11 pi over 12 radians is 165 degrees. Now I want you to think with me for just a minute. And let's make sure we kind of get a visual on this. I'm going to take you back to this page for a second. Remember how we said a full circle is 2 pi radians. So half of a circle would be how many radians? Well, it's 180 degrees, which is the same as 1 pi, right? What we just converted was 11 pi over 12. Wouldn't that be just a little bit less than 1 pi? I mean, 11 twelfths is pretty close to being 1 whole pi, but it's a little bit less. Look at our angle measure that we got. Is 165, pretty close to 180, but it is a little less. Okay, so logically, that's a good answer. I'm pointing that out because sometimes you may find that you've made some sort of minor little computation error. And so always check yourself to see, is this reasonable? Would it, I mean, I know if it's 11 pi over 12, it ought to be something less than 180. So if you came up with 275 degrees, you ought to know something's off somewhere, okay? Now, let's do this one. Negative 7 pi over 6, we're going to multiply it by what? 180 over pi. Pi's are going to cancel. How many times would 6 go into 180? 30 times. And negative 7 times 30 is, that's it, negative 210 degrees. It's really not that hard to do the conversions, is it, once you know the process? And then how are we going to change this, which doesn't have a pi in it, into degrees? Now, what does it mean if I don't see pi? It means they actually use the decimal approximation for pi to give us an approximate value in radians, okay? It's been rounded. Do we still use the conversion? Yes, we do. Now, watch what you would have to do here. Since that had already used the conversion from the calculator for pi into some decimal number, we're going to have to also put pi in the calculator and use the decimal approximation when we clean this up. So here's what's going to happen. If we take 2.92, and I'm not going to worry about the negative, I'll just put it on my answer, and I multiply that times 180, hit enter. But then I divide by, and I'll hit second, and the caret key, which is, some people call it rooftop, and hit enter. This is going to be how many degrees?
167.30.
Yeah, and remember, there was a negative here, so it's actually a negative 167 point, and since there were 2 places to the right, if we round 2 places to the right, you are correct, it would be 30 degrees. Okay? All right, questions on any of that? Is that good? All right, let's look at the next page. Notice what this says in bold italics. If no unit of angle measure is specified, then the angle is understood to be measured in radians. Here's what that means. If you do not see degrees right after this, then that means it's got to be a radian measure. Okay, now if it's a radian measure, it's probably not going to be nearly as large as the numbers you would expect to see with degrees. Okay, they're going to be small numbers. But most of the time when they give us diagrams, the diagrams are probably going to be done in degrees. But let's see if we can take those special right angle measures that we use in our right triangles and see what they would actually look like in radian measures. So we want to get an equivalent conversion for 30, 60, and 45 degrees. Okay, plus we probably ought to think about those quadrantal angles. So that's what this table is for, is to help us think our way through that. Now, 0 degrees, that's an easy one because it's going to be 0 all the way across the board. But a 30-degree measure, let's see if we can change it to radians. So to change it to radians, I multiply by what? All right, so I'm going to do 30 degrees times pi over 180 degrees. What does that turn into? How many radians exactly? You got it. Pi over 6, because we would reduce down the 30 over 180, and that would give us 1 over 6 to multiply times the pi. And then the approximate, just to show you, if we put this in the calculator, and we did, pi divided by 6, that's about 0.52 radians, okay? 45. Let's get an exact measure in radians on that. So what happens if you do 45 times pi over 180? You're going to get, how many times? 3. Isn't it pi over 4? Yeah, 180 divided by 45 will go, that'll be 4. The 45 goes into 180 4 times. So pi over 4 is the exact value for radian measure on a 45-degree angle. Now, tell me what that is approximately. So I want you to use the pi key on your calculator and tell me what you get when you do pi divided by 4. Good, that is about 0.79 if we need an approximation. Now this is given to us in radian form, and we're supposed to figure out the degree measure. So pi over 3 is going to be how many degrees? Good, because I would multiply that times 180 over pi. And 3 goes into 180 60 times. My pi's cancel. And then tell me what your approximation is if you do pi divided by 3 in the calculator. We are finally above 1 radian at 60 degrees, okay? Because remember, the 1 radian is going to be the distance on the circle that matches the distance of the radius, okay? All right, let's look at a 90-degree angle. That's a quadrantal angle. So at 90 degrees, what would that be in radians? 90 times pi over 180 becomes pi over 2. Very good. Pi over 2 radians is the same as 90 degrees. Give me a decimal approximation for that. I think it's 1.57, which is kind of logical if you think about, we normally use 3.14 for pi, so half of that would be 1.57. Okay, I see the 3.14 here. What did we say that's equivalent to? Pi, which must be the same as how many degrees? 180. Very good. If we took pi and we multiplied it times 180 over pi, clearly the pi's cancel and you are left with 180. All right, I want you to change 270 and 360. I'm going to give you just a second to do that and we'll see what you get. Okay, so what was 270 when you put it in radians? Isn't it 3 pi over 2? Because if we take 270 times pi over 180, then I know 60 goes, no, let's see, not 60, 90. 90 goes into 182 times, 90 goes into 273 times. And that's how we get 3 pi over 2, which is about 4.71 approximate. And 360 is what exactly in radians? 2 pi. So we had talked about 360 is the same as 2 pi. And 2 pi radians, if I multiply 3.14 times 2, I get 6.28, right? Okay, so that gives us a little practice on the conversions. It's not that you have to have this memorized, because as long as you know how to find it, you can do that. What you should discover, though, is these are probably going to be things you use often enough, you're going to memorize them just because of the frequency that you're using them. You know how you do things over and over and it kind of sticks? That should be what happens. But make sure you don't forget how to use the conversion. Now, this is called a unit circle. And I actually have a handout that I will give you next class that the title on it says Trig Cheat Sheet, which is a terrible name because I don't want you to think of it as a cheat sheet, but it will provide some of the key information you need to know in order to do the things we're going to be doing in Trig. So it's sort of like your formula sheet, your resource for finding things. The first test, I didn't want you to have access to anything like that because I want you to learn what those ratios are for all 6 trig ratios, and I wanted you to know those Pythagorean identities, but we're going to be learning enough stuff that you kind of need some resources to help you. And this is one of the things that some people do reference. I personally don't. I'd rather just do my conversion and find it myself, but you may find this is helpful for you because you can go through all 4 quadrants here and all of those special angles, depending on which quadrant you're in, they're providing not only the angle measure, but the radian measure for you. So you can easily change 225 degrees into radians off of the unit circle conversion, okay? So you might want to reference this some on the homework until you get more comfortable with it. And let's talk for a second about arc length. We used S earlier in defining what a radian was, that arc length measure divided by the radius. And so S simply means it is the length of that arc that is intercepted on a circle of radius length R by a central angle of measure theta radians. And if you were to multiply the radius and the radian measure of the angle, that would give you S. Now, that's a heck of a lot of words to say something that's really pretty basic. Here's the idea. If I know what my angle measure is, and I multiply it times the radius length, that's going to tell me how long my arc is. Now, think about it. If you're in radians, okay? Let's say that my radius is 1 because we're working with a unit circle. And if I'm working in a unit circle and I'm using radians, let's say it was a 60-degree angle, and a 60-degree angle would be what in radians? Pi over 3. What this would tell me is if it's a unit circle and my radius is 1, that's what makes it a unit circle, and I multiply it times an angle measure of pi over 3, guess how long that arc length is? Exactly, and that was our definition of how we were finding those radians, right? Because if I were to take that, I'm going to see that the angle measure and the arc length are going to match when I'm working in a unit circle. Now, if it's not a unit circle and my radius is a different length, this gives me a formula that will then let me compute what the arc length is, okay? Notice it says here, if you are using this formula, what would you think angle theta has to be expressed in? Degrees or radians? Got to be in radians, not degrees. Yeah?
Since we're working with radians, are we going to be changing our calculator?
Good question. Here's what you're going to find. You need to make sure you know on your calculator where that mode button is that lets you change units and how you round things and whatever else you may be needing to do in your calculator. And you will need to make sure you're set in the appropriate mode, whether it's degrees or radians, depending on what you're trying to do. So it won't be a one-time, we've changed it and we never go back. It'll be I've got to make sure I check this before I do this problem so I'm in the right unit. Good question. I'm sorry, what?
Oh, I know, I'm just looking around.
Oh, okay, just looking around. All right. So it's really important that we've got to remember using this formula, you've got to be in radians because you're not going to measure a length in degrees. That doesn't make any sense, does it? Okay. But we can measure it in radians. That's why it's such an important unit of measure because it is unitless. Okay, circle has a radius of 25.6 centimeters. We want to find the length of the arc intercepted by a central angle having each of the following measures. So if we have a central angle of 7 pi over 8 radians, can you tell me what would be the arc length that it cuts off of the circle? 7 pi over 8 is not one of our standard measures that we have up here, but I know 7 pi over 8's got to be somewhere between here and here. Wouldn't you agree? Because 5 over 6 is not as large as 7 over 8, but neither one of them are quite a full pi. So I want to know basically what's going to be this distance around the circle when the radius of the circle is 25.6 centimeters. Is this the formula I need? Yes, it is. So S would equal my R times theta. What did they give us for the radius? 25.6 centimeters. And what are we going to put in for pi? I'm sorry, not for pi, for theta, the angle measure. 7 pi over 8. Okay, now, if we're going to multiply that together and get a length, there's two different ways we can express it. We can express it exactly, and if we express it exactly, what will still be in our answer? Pi, the symbol pi. We can also give a decimal approximation because that's probably going to be most useful in the real world. Because if you pull out your tape measure, you don't see a pi on there, do you? Okay, so yeah, we would need to give a decimal approximation. So you want to give, in the habit of giving both, write it first where pi is still in the answer, and then we'll turn it into the decimal approximation. So if I were to take my 25.6 and, well, first multiply it times 7, and then divide it by 8, I'm getting 22.4 times pi. Does that make sense? And remember, I still have the unit of centimeters. This thing is unitless, but this one is not. So that means it's 22.4 pi centimeters for the distance of the arc, which is approximately, what would I do now? Multiply it times the pi button in the calculator. And when I do that, I would tell someone if they're trying to measure it off, it's about how many centimeters? 70.37 centimeters. Good job. Okay. What would be the only thing that we'd have to do a little differently to do B? Say it one more time. Exactly. I can't do what I just did with my formula until I convert these degrees to radians. So let's do that first. I would have to multiply by what to get it into radians? Yes. And at this point, you can decide if you want to go ahead and reduce this down. I mean, if it cleaned up nicely, you can. But since we're really just kind of plugging into the formula, could we just put 54 pi over 180 in the formula and then do all the cleanup later? I think you can. I mean, that to me would be easier to do it that way. So if I'm plugging in here, I have my 25.6 centimeters that I want to multiply times 54 pi over 180. So let's get the exact measure. You guys tell me what you come up with that should include a pi in it. Y'all getting 7.68 pi? Let's see if we come up with that together. 25.6 times 54, and then we're going to divide that by 180. And yes, I'm getting 7.68 times pi. So to get the decimal approximation, multiply that times pi from the calculator, and we would tell somebody that's about how much? 24.13 centimeters. All right, so far so good? Good deal. All right, let's look at this. You've got a rope being wound around a drum, and the radius of the drum is 0.327 meters. How much rope will be wound around the drum if the drum is rotated through an angle of 132.6 degrees? Okay, so you got a visual on what's going on with the problem? This thing is rotating, and it's almost like, think of it kind of like a bicycle chain, where it's got teeth, it's getting caught in it, and so it's going to swing it around. You know, this is not necessarily a bicycle chain, because it says it's a drum, but it's like you're winding it up, okay? Kind of like you wind up your garden hose. Yeah, kind of like a sprocket on a bicycle. So could we figure out what would be this length of rope that is now wound up on the drum? Using the formula we just discovered? Yes, we should be able to. Let's see if we've got all the pieces, because I know S is going to be that sector length. What did they tell me the radius is? Okay, my radius is 0.327, but what did they tell me that the angle measure is? So I'm going to have to do what with that? Convert it to radians. So we can do what we did a minute ago. We can actually put the conversion in and do all the cleanup together. So we would put in the 0.327 meters for the radius. And then for the angle measure, tell me how you'd write this down. If I put the 132.6, I got to multiply it times what? Good. Pi over 180. All right. So let's do it first where you keep pi in the answer to get an exact value. Let's see what you come up with. And I would say expect about 5 places to the right of the decimal. You guys got it yet? Are you getting something that looks like that?
Yes.
Excellent. But it needs a pi with it, doesn't it? So that would be 0.24089 pi. And what's my unit? Meters. Don't lose your unit, which is going to be about, multiply that times the calculator approximation for pi. That's going to be about, let's go 3 places to the right of the decimal on this one, because our original problem went 3 places to the right. That's about 0.757 meters. Good job. Okay. Now, we've got one more example I think we'll look at, and then we'll probably pick up with area of a sector, which is going to be the back page of this when you guys come back next time. So this one, here's your sprocket question. You got 2 gears adjusted so that the smaller gear drives the larger one, as shown in the figure. If the smaller gear rotates through an angle of 150 degrees, through how many degrees will the larger gear rotate? Now, any 10-speed bike riders in here, or anybody really into biking? All right, okay. So you have a lot of these things on a bicycle, do you not? Because as you shift gears, what does it do?
Moves the chain down.
Moves the chain from one gear to another. And the reason you do that is why?
Change the torque.
Okay, because if, say, you're pedaling up a hill, what would you want? If you're pedaling up a hill, would you want to have where you have to pedal harder to move the bike, or where you can pedal faster? Okay, and when you say less revolutions, if I'm pedaling faster but I'm on the right gear, what's it going to do?
It's producing more torque at a less revolutions per minute.
Okay.
And whatever the ratio.
In other words, I'm not as efficient if I'm pedaling faster, but it's an easier pedal than if I'm trying to pedal hard and I'm going up a hill. It takes a lot more effort on my part. Does that make sense? I don't know if you guys really thought about the way those gears work. You guys have done a good job of explaining that. But the idea is, depending on where that chain is placed, on which size sprocket, that's going to affect how efficient my pedaling is, how many revolutions per minute I'm going to get, and ultimately will determine how easily I move up the hill, or if I'm on a flat surface, I probably want to do what?
So you're exerting more energy to use.
Because I would be more efficient then exerting a little more energy, because I could actually move a lot faster. Trying to exert that extra energy up the hill is probably going to be counterproductive for most of us. All right, good deal. So if we look at this and we know the smaller gear is going through an angle of 150, why are they asking us through how many degrees will the larger gear rotate? Isn't it going to be 150?
No.
No, it's not, okay? Because the way these things are connected, think about it, as this thing, like you picture right here, if this thing starts rotating, okay, this hooks in here and this will hook in here. If this thing spins all the way around one time, will it have had an opportunity to spin around one full revolution on the thing? No. That's why the angle measure is not going to be the same. So I got to figure out, if I go 150 degrees here, how many degrees will that have caused the larger ones to go? All right. So let's look at this and see if we can figure out how to start. What do you think? First of all, do you kind of see the need for maybe two problems in one? Sort of like when we did this, and we had two triangles, and we had to solve in one triangle to get something to help us solve in the other one. Is this one kind of like that? Okay, so tell me how you think you would start.
Start with the smaller.
Let's start with a smaller gear, because that's the one they gave us some information on. And in the smaller gear, what do we know? And I'm going to assume at this point, because it's the first section and we have one formula we've been working with, somehow this is going to come into play, is it not? Okay, so what information have they told me about the smaller gear? I know the angle measure, that it's going to rotate through. What else do I know? I know the radius. That's enough for me to figure out the sector length, is it not? All right, so let's do that. And we will have my radius of 3.6 inches. And my angle measure is 150. Now, if you want to pull it off of your unit conversion, you can. But we could also do 150 times what? Pi over 180, and we can just kind of clean it up in the calculator at one time if you want. Okay, so let's keep it exact. Let's end up not putting in a decimal approximation for pi. So multiply this out and tell me what you're going to end up with for your sector length. 3 pi. Very good. If you were to multiply 3.6 times 150 and then divide it by 180, that's where the 3 came from. And so we have 3 times pi, and that's in inches, right? Now, that means the distance this thing is rotated when it's gone 150 degrees is 3 pi inches. Now, how am I going to, what is it I want to find on the larger gear? The angle measure that it would have rotated through. What do I know from the larger gear other than the radius? You're on the right track. Let's keep going with it. If this thing has moved 3 pi radians on the sector, well, this has also moved 3 pi radians. The sector length has to be the same. It's the angle measure that's going to be different. Does that make sense? So it's the same formula, but now we're going to plug in for S. And what are we going to plug in? 3 pi. And I know the radius because the radius was how much on the larger gear? 5.4 inches. And then I'll find my angle measure, theta. How do I do that? Yes, I would. I need to divide by 5.4. And that's going to give me what? Three divided by 5.4 is it, okay, so it would be about 0.56 pi, you think? And that's not in degrees, but can I change it to degrees? By multiplying by 180 over pi, so that the pi's will cancel, and that's going to be about how many degrees? If we went to the nearest degree, since this one was rounded to the nearest degree, it would be about 100 degrees, wouldn't it? And that makes sense, doesn't it? It should be a smaller angle measure in a larger gear than it was in the smaller gear. Okay, we good? So the only thing we have left in this section 1, we'll be talking about area of a sector of a circle, and it's not going to take long to do that. But what that means is I'm going to open up your homework in 6-1, and you'll be able to start on it, but there could be a problem or two at the end.